bit today about new processes for water and wastewater operators out there everywhere. I'm sure there's a couple of engineers sitting in the room, so we won't pick on you guys too badly. I'm not an engineer, and I'm pleased to say that. And I can't get this thing to work, so let me do this.
There you go.
So I'm a 39-year veteran of the water wars. I started out my career in the city of Winnipeg, and I started out in the ditch, and I finally finished up as the supervisor of maintenance for the city of Winnipeg. So I went from ditch to bitch. And at my retirement party, it's basically, hurrah, see you later, on to the next flunky is the way that the men felt, because change is always happening in our workplace. As municipal employees, I've seen many, many changes, but this era that we're in right now is the most dynamic era for technology change and different work practices, and us moving from you know, the unsung hero of municipal service to becoming full-fledged operators, public health officials, hydraulic experts. So your job is very varied and it's very important. And so I know where you're coming from because I've sat in that room too. So I own my own company, and I work for a company now called Echologics Engineering. And Echologics Engineering was recently purchased by Mueller Company. So if you have Mueller hydrants or Mueller valves or Mueller brass in the ground, that's Doug Kalinowski. He's your local area Mueller rep. And we're a subsidiary of Mueller. So the big American company went out and bought a really sharp Canadian company. And we're really happy to be part of their team. And I represent the western part of Canada and some American states, but I also am the national distribution manager for Echologics. So I get all of our products into distributor sites like Minnesota Pipe here in Minnesota. They carry our leak detection products. So, today we're going to talk about condition assessment methods. And what we're talking about is I've got pipe in the ground, and everybody talks about infrastructure deficit like it's this great big scary machine out there, something that's going to overtake us someday. The infrastructure deficit of the water system or the utility, and in fact infrastructure deficit is something that can be dealt with in a measured, calculated way using science today. It doesn't have to be a pick and a poke on which pipe you're replacing next. You can make some really good decisions as operators to save yourself some time down the road. We're going to talk a little bit about Echologics and the new technology that was developed by our own National Research Center, the host of geeks that we have in a building in Ottawa, Canada, that we could go to and throw specific problems at them in regards to water and wastewater industry, and they study these things and come back with answers for us. We're going to talk about some case studies, some recent projects, and we're going to do some serviceable lifetime predictions for water mains. Because if I know the condition of the pipe and ground, what I want to know as an operator is how much longer is it going to last? Where's my next set of problems going to be in my town or city? And then we'll talk about a summary of value, and then there's a little portion in there on some leak detection methods that we've developed that far surpass some of the things that are available on the market today, because all of the technologies that we're seeing, that I saw out there as an operator working for the city of Winnipeg, didn't do the job for me. So we've gone to great lengths as operators to marry the ideas, the smart field ideas, and put them into the hands of the geeks and make them come out with the products for us. So it was really a great experience for me over the last 11 years, because as a municipal employee, you're always sitting here saying, what if? And I got to, not only what if, but I got to participate in the development of some pretty neat technology. So condition assessment. I remember, I'm so old, I remember when the sewer camera was invented. How many people are old enough to remember when the first sewer cameras came into this business? So inspection of a collector sewer or a domestic sewer in a town, city, or village was done by climbing down a manhole and having a look down the pipe and see if it was okay. Or we had rods in those days. We used to push the rods down to clear the sewer out. We didn't even have sewer jets. So we did very little preventative maintenance on sewer systems, and until the camera was brought in, technology, we really didn't have a way of calculating what kind of damage was being done to the inside of the sewer system. But since that time, every city and town budgets for spot repairs on sewers. And they do that based on science and technology. They have a visual look, they see that there's a problem with the sewer, they budget the cash to do the job. I'm sure that every one of you have small sewer jobs that you have in the budget for next year to do as a result of a televising campaign that was done in your town or city. So in the waterworks industry, we've always been technology adopters. But we haven't had a lot of technology come our way. Operators are always self-educating. We come to things like this to self-educate and learn the newest technologies. So we're not against learning something new or a new system. Just a lot of times we don't get the opportunity. So, current inspection methods for water systems is visual inspection or CCTV or manned entry, sampling of the pipe, which they dig a hole, cut a piece of pipe out, send it out to a lab. It's very invasive. The sample that they gather only represents the pipe condition in the dig zone, and we just had a small conversation here a few minutes ago with one of the members, and he said, how come I can dig out a piece of pipe in one piece, and it's in bad shape, and I go to the next section of the pipe and I can see all the lettering on it, the coal tar on it is still in perfect shape. It's an environmental condition. Everything we put in the ground is going to turn to dust eventually. The trick is to try and predict when it's going to break down and how quickly we have to replace it with something else before it becomes a problem for us. So we want to use non-destructive testing. That's what we're trying to do. As a distribution operator, when somebody came into my town with a great idea to help me out, but they said I had to slip something into your water system, I was against it from the very get-go. Because I know that when I'm slipping something into my water system, I'm potentially creating a whole new host of problems for myself. Dirty water, broken valves, all the ancillary problems that happen when I start going inside of a water system. So we wanted to do some checking and see if we could find a way to do it without being destructive, without being invasive. So there are indirect methods. There's predictive software models where they take the age of your pipe and they try and do some prediction on when it's going to break down. But it's really just a shot in the dark at that point. They use failure history to do replacement. You may have fixed the leaks in that section of pipe and the rest of it may be in very good shape, but because it reached a certain amount of leaks on it, it automatically falls into the category of replace the whole block. In essence, you may have solved your own problem already by fixing the leaks in the areas that you did, and the rest of the pipe may have some significant remaining life in it, but you don't know that because you don't have science to attach to it. We look at leakage levels, people do flow testing, and soil resistivity tests are done because we know in Manitoba, like in Minnesota, like in North Dakota, like pretty much everywhere in the world, we have hot soils. We have soil resistivity that attacks anything metal in the ground. And in fact, anything that is made of asbestos cement in the ground is attacked by the ground. So nothing is immune to it, except for CPVC because the jury's still not out. It hasn't been in the ground for 100 years. What's the oldest system that anybody has in this room? Over 100 years? Hands up. Over 100 years over there. So that pipe's been in the ground, invisible, for over 100 years, and we have no idea what the condition is unless we dig it out, correct? That's invasive. So when they do pipe sampling programs, what they do is they check the thickness values based on the exude samples, and it may not be representative of the pipe all the way along or in a neighborhood. It may be just that piece. So that's costly and disruptive. There's a system known as remote field eddy current system, where they launch pigs inside the pipe, and they're smart pigs, not ice pigs. First they have to scrape all the pipe out, then they have to send the machine into the pipe, again invasive, and I had it done in 1996 in the city of Winnipeg, and we ended up with 30 water main breaks post putting the pig through to determine the pipe wall thickness. So in a world where I came to the city of Winnipeg in 1974, we averaged about 2,600 water main breaks a year. So when I talk to you about water breaks and things that I know, it's not because I'm any smarter than anybody else in this room. I'm like a trained chimp. They just kept sending me to the next location to repeat the process and the next one. So living under that situation, you try to learn things as quickly as possible to make your job easier. So they put these pigs in, and then we've got this whole process of gathering the data back once they come out. This technology has been used in the gas and oil industry for years. They check gas mains this way. It's very costly and very expensive. It is effective, but very costly and invasive. So we want to know the remaining pipe wall thickness because it's a direct indicator of structural condition. Pipes are in constant movement underground. Pipes are constantly breathing outward and inward as pressure is put onto the system or released from the system. So every time the pump kicks in, every time the tower fills a section, the pipe is microscopically moving outwards and inwards. Then in Minnesota, like we do in Manitoba, we have ground conditions that make the pipe want to torque. Frost heaves it up and down, moves it slightly. All these things are aggressive to the pipe in the ground, so it's never sitting there dormant. It's constantly in motion. We lose effective thickness on metallic pipes due to corrosion. We lose effective thickness of asbestos cement pipe because of waters leaching into the outer coating, removing the calcium, which is the binding agent, the cement, and leaving it with just silica sand and asbestos. And on the inside, we've just discovered that we have a bad friend that lives inside our asbestos cement pipes. And it feels like a biofilm when you empty the pipe out. And that biofilm is a non-pathogenic microbe that eats calcium, that eats cement. And so what's happening is we're losing the pipe wall thickness on AC pipe, both outer and inner, at almost the same rate. Because this little bugger eats really, really well. PCCP pipes, if you have them, pre-stressed concrete pipes, lose strength when the concrete weakens and the pre-stressed wires break. And plastic pipes lose strength after chemical attack. Like any piece of plastic, the longer it remains dormant, the harder it gets. And the same thing falls true today for our CPVC pipe. I was mentioning that it's been around now since 1938, but it was a German scientist that invented it in 1938. Then his boss went out and invaded Poland, started a world war, and nobody talked to the Germans until 1952. We ended up with CPVC pipe in Winnipeg for the first time in 1954. And so we've gradually been taking pipe samples off that pipe that's been in the ground since 54. And we see no appreciable difference in the pipe, the quality of the pipe, and any chemical changes to it from that time. So it's pretty sturdy stuff. And I'm not a pipe salesman. So what we wanted to do is we wanted to find degraded pipes and then at the same time do leak detection for people. Because we had invented a piece of leak detection equipment that could do the calculations that were required to determine the wall thickness of pipe underground without digging it up or turning it off. So towns and cities said, well, that's the same machine that you use for leak detection. Why don't you do leak detection for us at the same time? So we said, okay, we'll do it. So any of the leakage that's found during these condition assessments generates returns on the engineering costs. And the worst pipes are prioritized for rehab or replacement. If you think about the larger pipes on your system, if you have large, who's got pipes larger than 18-inch on your system? Significantly larger leaks occur on larger pipes. It makes perfect sense. What's the pressure on your large pipe? 58, somewhere like that. So have you had any leaks on it yet?
Oh, yeah.
Yeah? They're significant. The water loss from them is just, it's horrific. And the damage to properties is a lot. So we wanted to mitigate the damage by qualifying the condition of large diameter pipes. This is where the technology came from because of some large diameter pipe breaks that we'd had up in Canada. This is where the question came from, how do we do this? Because of the damage that was caused because of these leaks. And I've got some pictures of them. So how we do it is, we measure how quickly a low frequency acoustic signal is transmitted along a section of pipe. Now that sounds kind of geeky and I'm going to get ungeeky for you. If I have a piece of 6-inch pipe sitting right out in front of me right now, and I hit it right here, the sound will travel down it at approximately 4,000 feet per second. If the pipe is losing iron content, which provides the ring through the pipe, if it's losing iron content and we're losing iron in that pipe and it's rotting in the ground, the signal transfer will be slower. What we measure is the difference between the two signals. We know what the signal was when the pipe went in 100 years ago, because we've done enough exhumations of those pipes. And we know what it is today based on the science that we apply to it. And the difference between those two numbers is the generated value of how much pipe wall loss there is there. So that's an important thing to know, because we'll keep talking about that. So we want to know the average pipe wall loss over a distance. Because in the water business, we don't replace pipe inch by inch. When we decide to take a pipe out and go to the extreme measure of replacing a water main, we do it on a block by block basis. So we want to know the general condition of the pipe on that block, and we want to qualify it against all the other blocks in my city. Where's my worst pipe? Where's my best pipe? And then you start to eat the elephant. The elephant known as infrastructure deficit can be eaten, but you got to eat it one bite at a time. And you can't do that unless you apply some science. Otherwise, you're just digging up pipe for the sake of digging up pipe. So, this is Kiki. I'm moving on. So, this is what your pipe looks like in the ground. This is a cast iron pipe. I'm going to move off the mic. Can you all hear me okay? Yeah?
You got this one working?
You got that one working?
Yep.
Nice. Can you hear me?
Here's the button I push on.
Okay. Can you hear me okay? Is it working? Yeah. Okay, so this is what the oblong of a cast iron pipe looks like. When you take it out of the ground, if you were to slice a piece off it and look straight on it, this is what it looks like. This is the pipe that has gone away. That's all rough on the outside. This is the pipe as it's gone away. This is the remaining pipe wall that's inside there. And this is tuberculation, of course, that's inside the pipe. So we try to determine the thickness of the remaining wall of that pipe when we're out there. And that's critical to this process, because if we don't know the thickness of the pipe, we can't tell the end of life cycle on it. The pipe will only restrict so much pressure this way, and will only restrict so much pressure this way by having so much pipe wall, in fact, left. So that's the minimum band of continuous metal. The raised areas can no longer carry a load, because that's all carbon now. Like I said, everything we put in the ground is going to go back to the ground. So we do it by simply racing a sound between two sensors and measuring the speed of that sound. So no invasion of the system. We can either tap on the hydrant on the far right, or we can flow water from it to get our calculation.
Get a laser on the top.
Oh, we got a laser on top. We got special effects.
Save you from walking.
So we can tap this fire hydrant to create noise across the two sensors to gather our data. Okay? Graphically, it's represented on our screen by that great big marker that you have up on the right. It's got an X to it. That's the actual velocity of that pipe. You don't want to have to do this calculation. It won't be on the test. All I know is after last night, it's a good thing there's no P-test. So we did a pilot project to test this technology in Hamilton, Ontario, because that's our country. We needed a water system that we could go in, test for wall thickness, condition, and then exhume it and have it tested in a lab to prove our theory. So we selected some pipes that were installed between 1860 and 1960, and the accuracy of the remaining thickness predicted based on visual appearance and average wall thickness of exhumed samples. Only one pipe in 1860 that was laid in 1860 was found to be in poor condition. So that kind of answers somebody's question over there. The only thing we're seeing with the older cast iron pipes is we're seeing lead joint leaks. And that's from the torquing action again. Over the years it raises and lowers. Put stress on the lead joints and we get a little lead joint leak. We might get a leak in a corporation or something like that. But we're not seeing the type of massive failure in old cast iron pipes that we saw with ductile iron pipe that we put in the ground in the early 70s. So it's an interesting statement that we're making at the bottom there. So this is what the pipes look like. These are exhumed sections. So you can see there's tuberculation in there. And that, I'm afraid, is what a lot of our cast iron pipe looks like in the ground. Now the question was during the last presentation is, will it take that tuberculation out, the ice stuff? No, I think it's more of a biofilm, isn't it?
Right.
Yeah. So this is what it looks like after we've exhumed it and sandblasted it now. So you can see the pitting that's occurring on that pipe. So if I go back here and you take a look at it, you'll see that in this area here, this is almost worn right through. There's another area here that's almost worn right through. So when you're thinking about that flex factor in that pipe, that microscopic flexing, as the iron gets leached out of there, that's when the pothole is going to occur. And then the small hole becomes a large hole as water goes through it. So, there's your piece of pipe. After we take all the crud off the outside of it, we find out we've got lots of leakage to it. That's after we blasted the inside and the outside. So basically all that's holding it together is the crud. So this is the exhumation samples of an 18-inch water main. So this is what it looks like coming out of the ground. Doesn't look that bad. And this is what it looks like in real life. So the funny thing is that we learned was this is the bottom of the pipe. So this is the bottom of the trench. And we see that consistently everywhere. We think the reason for it is it's a rubbing action that occurs. It's the most weight-loaded portion of the pipe. So as the pipe is moving microscopically in the ground, it's actually wearing away at the bottom of it. That's the inside of the pipe. Am I going backwards? No.
There you go.
This pipe was put in 18-inch was 1860. And you can see there's still significant pipe wall to it. Oh. There's still significant pipe wall to it. You'll notice that the outer sections are still quite thick even after it's been sandblasted, but there's still significant pitting going on in all areas of the pipe, and there's no consistency to the pitting. And the next section might have less, and the next section might have more. So, we discovered a service leak. We took 3 coupon samples, and some of the pipes were selected for relining. This is Newark, New Jersey. This was a big project in Newark. So there's the inside of the pipe. Now if you want to look very carefully at this, you'll see what I mean. This is the remaining pipe wall of this pipe. When you take that pipe and you dig it out and you start scraping it off, you think it's not in very bad shape. It's in pretty good shape. But essentially all this is carbon, because the iron has been leached out of it. There's nothing left there. So there's your next water main break about to occur. Tuberculation and graphitization do not contribute to structural thickness. Graphitization is when the iron is leached out of it, and you get down there with a file to clean the pipe off, and you keep scraping and scraping and scraping, and you say to your buddy, I don't think I'm going to have any pipe to connect to here, because I just keep scraping all this graphite off. So there's the actual wall thickness, and it's very thin. This is how it was done in the residential area, which is really kind of cool because we don't come out with a lot of equipment. We come out with a couple of small vans and a couple of service keys. Las Vegas, Nevada, we work there constantly. Water in Nevada, as many of you know, is like gold. They got serious water problems. They recycle wastewater. They do all kinds of stuff with water, but the one thing they don't do is waste it. It's like a SWAT team when they have a water main break there. If you run your sprinkler on the wrong day there, you get a hell of a fine. So they brought us in to determine the quality of their AC pipe, and we found some pretty interesting stuff. How many people have AC on their system? Asbestos cement, paper pipe. Thanks, lots here. Okay? So that's Las Vegas Boulevard. A 2-week job turned into a 3-week job because of the dancers. So when we look at AC pipe, and this is something that every one of you people will agree with me, when I dig it out and I take a look at it when it's sitting in the bottom of the ditch, it looks like it's brand new. It looks like the day it was put in. All those dimples are perfect on it. There can't be anything wrong with this pipe. Well, there is. That's what the pipe looks like. When you stain asbestos cement pipe with phenol phthalate solution, the pink chemical attaches only to calcium. So everywhere the calcium is gone, everywhere the cement binding agent is gone, it won't show pink. And there's the pipe itself. And you can see that the remaining wall on the outside is losing calcium to exterior forces in the ground. And on the inside, there's my friend the micro. And he lives everywhere. He doesn't have a home base. He don't care where he lives. He don't care if you're from Canada or the US. He'll eat your pipe. He's just non-discriminate about that. So there's the inside of the pipe being eaten away, and the rest of the pipe wall is the strength that allows AC pipe to be able to resist those torquing actions that happen when we get freeze and thaw cycles, or dry cycles, right? We get lots of AC leaks when it's really, really dry, because the ground is moving, it's contracting. So we ended up with a 5-year renewable contract with them. We're doing all of their AC pipe because they want to know which ones to replace. They know they've got a big bill coming, but they want to know exactly how to eat the elephant, one piece at a time. So here's the lab results. This is what the pipe looks like. These are all the crush tests that we do. And that's the actual pipe. Now it's blown up again for you. There's the outer layer of the pipe, and you can see that there's no staining attaching to the outer layer because in this area here there's no calcium left to bind the pipe together. And here's my friend the micro on the inside. That's a cross section. In Louisville, Kentucky, we tested a 76-year-old 24-inch cast iron pipe. They were going to take it out of service. And we did 13 technologies competed in this thing. So we ended up winning it. It was kind of fun. It's a leak detection rodeo. You guys in the States, you'll find any reason to get together and have a competition. Trucks, swamp buggies, leak detectors. I'm telling you. It's great. So what we do is, once we get all of the pipes qualified, and we know what the wall thicknesses are throughout a whole community or a neighborhood, we then throw the pipes up on the wall for the politicians and the decision makers to see it. And they see that the red sections are your very worst. The yellow sections could be rehabbed. We can do some lining, we can do some cathodic protection. And the green ones are in really good shape. We don't have to worry about those for a long time. So now the elephant's in 3 pieces. And now they can start chunking away at the red sections. And they can get a plan over the next 25 or 30 years. Because the same way we applied science and technology to spot sewer repairs, we can do the same thing for our water main renewals and not have to go through all this head scratching when it's time to get this work done. I find that more often than not, we fail as operators in getting our point across about renewing certain sections of the water main because we don't have empirical data in our hands. And the engineers above us and the decision-making politicians don't want to take our word that the pipe itself is in bad enough shape to be replaced. When you do these things and you attach science and technology to them, it carries a lot more weight and credence when it comes to making the big decision in the council chamber about how much money we're going to spend on water main replacement. So, I wanted to go back one. There's one slide that I want to talk about. When we talk about corrosion on pipe, metallic pipes degrade via corrosion and it's not uniform. And the one thing that I found out over the last year was, I couldn't figure out for myself why ductile iron pipe only lasted 20 years in the ground in the city of Winnipeg. It literally ate holes into it and there's nothing left of it. We would dig it up, have to take 12, 15 feet of it out before we could find 2 pieces to connect it. And the reason simply for it is it's part of the manufacturing process. And I'm not knocking them, they do what they do. But in the manufacturing of ductile iron pipe, they don't use a consistent metal to make it. Could be old cars, dryers, whatever it is that goes in that day. It's founded into molten metal. And the steel comes out and is spun onto the casting. Now, the wall thickness of the pipe is dependent on how fast the guy spins it. Individually, he can spin it faster than another guy. And how it really reacts when it starts cooling down is up to the guy on how long he cools it down for. So the thing with ductile iron pipe I found out was there's no consistent wall thickness to it. And a lot of times when you're looking at it or running your hand down it, it feels kind of bumpy. And it doesn't feel like it's straight all the way along, like you would with a piece of AC pipe or a piece of PVC pipe. And that's why they put that coal tar on it, to give it a uniform look, essentially. But the wall thickness is not the same throughout. So there are pockets of higher grade and lower grade steel throughout the pipe all the way through it. And when we talk about those degrading issues, soil resistivity, all those things, grounding every electric service to our water system, all of those things affect the way pipe reacts in the ground. And cast and ductile are the first to go. Well, first the bolts. If there's big iron bolts down there, they go first, and then goes the cast and the ductile iron, and then after that goes the copper services, or the lead services, because there's a pecking order to how things react in the ground. And soil resistivity affects all of those things. So we've had less ductile iron success in Winnipeg, and I don't know what your success rate is like, but you go to places like Dayton, Ohio, and they swear by it. They put it in at phenomenal rates. They won't put in PVC pipe because they don't have the same soil conditions as we do. So it's an interesting thing about pipe. Geography is the only thing that separates us. Most of the time our problems are pretty much the same. Okay? Now, how many people do leak detection? Love it. Love it. A dying breed we are. About 200 of us across the continental United States. Some people do this, they listen on the ground with a probe. Some people do leak correlation where they're got two stations set up and they're using some electronics to do it. Some people locate by gas. We were talking about a leak on a farm service. Where's the fellow that's got the lady with the leak with the 2,700 gallon, $2,700 bill? So I did one a number of years ago in Melfort, Saskatchewan. It was 5.5 miles of 4-inch Belton spigot PVC pipe, and there was a leak on it. And the city of Melfort wanted it found, so I had to helium-induce the pipe and then walk for 2 days across a canola field till the helium detector detected the helium coming out of the ground. Because that's the only way you can do it. Gas is a very great way of doing it, but it has to be safe for humans, which helium is, and helium forms a gas bubble that comes out of the ground. Now that's great in the summertime, but you can't do it in the winter. So you can trace by gas. People have been looking, has anybody tried ground penetrating radar? It's good to about 18 inches, so that doesn't help us with our 8-foot buries. So people have listening equipment out there. How many people recognize these? How about the old pucks? Anybody got the old pucks? You got pucks? Pucks? Really? They're good. 1930.
Yeah.
Sorry. I'm almost that old.
They're in the museum.
The Museum of Modern Water History. So if we have unamplified devices like the one we saw, a screwdriver, a mechanic stethoscope, the little hearing devices, or those pucks, they're kind of simple. They're easy to fix. Some people make them themselves. You know, a couple of toilet plungers, whatever you want to do. Witching sticks. How many people do witching sticks? Really? Are you any good at it, or are you just out there farting around?
Very good.
You're very good at it?
Yeah.
Get out of here. I'll get you to tell my fortune later. No, I don't disagree with you. Some people have it. I don't have it.
Yeah.
I see them wandering around there with willow and wires.
Anybody in here? Who's in here? Can verify that. Where are they?
One.
Yeah.
I just left.
I don't get off my.
I don't dispute it. I don't dispute it. Honest to God, I don't dispute it. Adam and Eve. So you can make it yourself. It's cheap, light, can be robust. You know, you've got these things. Like a screwdriver is always handy. There's no electronics to it. You don't get any white noise out of a screwdriver. There's no battery to buy. But unamplified disadvantages are simply this. We need sound to detect leaks. We need to put these away and turn these on. We have a vested interest in our eyes. How many times I've gone to a job and the guy says, oh, that leak's right there. It's got to be right there. It was the last time, it was kind of the same leak. It was right there. The problem is our eyes lie to us constantly. And we try to make ourselves right by letting our eyes try to make this decision. And it's a bad choice, because sound is our best friend. Sound is transmitted throughout the water system from leakage. Unamplified disadvantages: if you're using a screwdriver, the interfering noises in the air can cause trouble. Sound will only be heard near the leak. Sounds cannot be heard with some pipe, and as long as you've got good hearing. So all that rock music, remember? Steppenwolf, Jimi Hendrix, right on, baby. Our ears are screwed. But the dope was good. I just had a flashback to the 70s. It was a good one. It was a good one. Yeah, tie-dye, girls running around in long dresses.
Headphones help.
Headphones help, yeah. So this is an amplified listening stick. So basically what this does is it amplifies over 100 times what you can hear off your screwdriver. So if I want to raise my game when it comes to locating leaks, and I want to take my eyes out of the equation, I've got to turn up my ears. Sounds on the hydrant, sounds on the valves, services. It's all over the place. It's up to you to determine the highest point of sound and assume that that can be the leak. So a leak listener works primarily the same as the other one I showed you, as a point and sound device. But then you can put it on the ground. You can put these things on the ground now and walk along with them and listen to the sound of the leak below ground. If the leak is on this area here, as you're walking towards the leak, the sound will elevate into your ears, and as you walk past it, you'll hear the sound starting to go away. That's a determination of a leak. That's how you find it. We have more intense equipment for people that have already had. How many people have this type of equipment already? We've got some sort of a listening device, electronic listening device. So you have a tuner-like device that you can put right on the ground? Yeah? It's awesome when you get to know how to do it.
Yeah, that's cool.
And the problem is that very few people can teach you how to do it. And it's always taken out in an emergency. There's always some doofus counselor standing there saying, hey, I bought that thing for you, how come you don't know how to use it? Right? Or some guy's running around with a machine scraping ice. So all those things impact our ability to hear it. The amplified advantages are very soft sounds can be heard, and we can hear loud sounds even further. So every hydrant on the system becomes a conduit of sound. So I get a situation where I get a small town and the guy says, I don't know where this leak is, but I'm losing 25,000 gallons a day. So I hustle out there and I jump on the first fire hydrant and I just keep taking hydrant, 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 and I'm hearing the same thing, the same thing, the same thing, and then all of a sudden I'll get something different. The anomaly is the sound of the leak on the system, and that's where I'm going to start to investigate this leak. But I can't do that unless I've got sound amplification on my side. Filters can remove unwanted noise. We now have sound dampening headphones. I remember when I started to operate this equipment back in the 80s, it was horrible, but it was the best we had at the time. When I started to learn this stuff, the equipment that we had was the best that you could get at the time. But we didn't have noise-canceling headphones and, better filters in equipment so that I would specifically be able to hear water and not hear what else is going on. Except for hotel rooms. They work very well in hotel rooms. You don't have to put the glass on the wall anymore. So a leak correlator is simply a machine that listens on the system for you. Uses a computer to determine where the leak is. How many people have seen a correlator work? How many people have a correlator? You have a correlator. Is it still working good?
Sometimes.
Is it the snowball? Use the correlator, right? Then take the snowball. Right? Because you're frustrated. No, don't feel embarrassed. Just be frustrated like I was. We'll talk after and I'll tell you why your correlator's not working. Okay? It's science. That's what it is. So correlators are very simple. They come with sensors. You put one at one end of the block, one at the other. And what it's doing is it's listening for vibration along the pipe, and it's listening for the highest point of vibration. And then all it does is it measures the time delay back. And it tells the correlator that it's 1/3 of a second from this end, and 2/3 of a second from this end. So I'm going to spot the location of the leak at almost this point here on the screen. And that's what a correlator does. We've made vast improvements in the area of correlators because operators became involved. If we leave this thing to sales and marketing, nothing gets done. But when operators get involved in the development and the improvement of a technology, we know what we want to see in the field. So when I became involved in this thing, it was interesting to me that I was the guy with the bright light on me and not the engineer. The engineer wanted to pick our brains because they wanted to solve the problem, and they knew the only way that they could do it was to understand what kind of pain we were going through in the field, why our correlators weren't reacting to leaks anymore, and why we were making mistakes and digging holes where they didn't have to be done at $7,000 a hole. Because that's what on average it costs to dig a hole now. About $7 grand to put the concrete or asphalt back in. So every time we miss a leak, it's a stain on us as the operator. Okay? There's going to be a picture coming up here. So that's basically what it's doing. There's your leak. So assume that this is a third of the way away. So the time delay is a third of a second this way, and it's 2/3 of a second that way. So it spots the leak on the computer screen at that point, using time delay from both ends. Very simple technology. And in fact, the correlation methods that's used today in the newest correlators is no different than it was back in 1985 and 84 when I started working with them.